All right, hello class. We are starting chapters 8 and 9, which are covering reactions to alkenes and alkynes. All right, to complete chapters 8 and 9, we need to learn 15 reactions to alkenes and 11 reactions to alkynes. All right, so all of our reactions in chapters 8 and 9 are classified as addition reactions. So typically there would be a double bond or a triple bond where we're adding atoms across that unsaturation. All right, this is the complete opposite of elimination, where there's atoms already attached to a molecule that are eliminated to form an alkene. All right, so there's going to be three things to keep in mind to keep track of all of these reactions. First, we need to know the chemical transformation. All right, so which reacting atoms are added across that pi bond. So we need to know the transformation type. All right, so there's a hydration type where we add water across double bonds. All right, there's a hydrohalogenation where we're adding a binary acid across a double bond, and typically that binary acid is going to have one hydrogen and some type of halogen. So HBr, HCl, HF, or HI are the typical hydrohalogenation reagents. All right, there's something called a hydroalkoxylation where we add an alcohol across our pi bond. All right, a dihydroxylation is going to create a diol. This is a molecule that has two OHs added to the starting reagent. Cyclopropionation is going to create a cyclopropane ring. Epoxidation is going to create an epoxide. We'll cover that reaction in detail a little bit later. Hydrogenation is going to add hydrogen atoms across that pi bond. Ozonolysis is going to add ozone across your pi bond, but overall adding ozone is going to do an oxidative cleavage, so the alkene or the alkyne is going to cleave in half. Halogenation is going to add halogens across your pi bond. All right, so if we can keep these transformations in mind, we'll be able to at least cover part 1 of learning all our reactions to kind of know which transformation is occurring first. Second, we need to think about the regional selectivity. All right, so which region on the double bond or triple bond is gating certain atoms. So we call this discussion of regional selectivity either undergoing a Markov-Nyakov addition or an anti-Markov-Nyakov addition. Okay, so let's talk about that in detail. So if we take this alkene and we're going to label the two atoms, or the two carbons, I'm so sorry, at the alkene, letter A and letter B, all right? Atom A is less substituted than atom B. And if you guys can tell here, atom A has one carbon block that's kind of in this circle, while carbon B will have two carbons attached to it, right? So being more substituted means I have more carbons attached. If I undergo a reaction where my new atom that's being added across my alkene ends up on carbon B, which is the more substituted side, we call that addition a Markov-Nyakov addition. Okay? Conversely, if we add an atom, or a reactant atom adds to carbon A in this case, which is our least substituted carbon, we call that a anti-Markov-Nyakov addition. So for all of the transformations given above, hydration, hydrohalogenation, hydroalkoxylation, dihydroxylation, cyclopropionation, epoxide, hydrogenation, ozonolysis, and halogenation, we want to also consider what regions are gaining things. Is there a Markov-Nyakov or an anti-Markov-Nyakov addition for each one of those classes of transformations? All right, and the third thing to consider is the control of the addition. Do all the adding atoms add to the same side or to opposite sides, or is there no control over how they add? So when things add to the same side, we call that a syn addition. So if we look at the example here, both adding atoms, the H and the X here, are both on wedges or both on a dash. All right. When the adding atoms add to opposite sides, we call this an anti-addition. So one atom here is either on a wedge and the opposite atom is on a dash, or the converse or the opposite of that, where one is on a dash and the other is on a wedge. Okay, so to master the reactions for this chapter, we need to consider all three things here for all reactions that we're going to learn. What is the first question you should ask? Which atoms are adding, or what atoms are adding? All right, so again, it could be water, alcohol, halogen, or a hydrohalogenation. I could be forming a cyclopropane ring, an epoxide, or doing some type of oxidative cleavage of a double bond. All right. The second thing you should ask is where. Where are these atoms adding? Okay. Are they undergoing a Markovnikov or anti-Markovnikov? All right. Or is there no consideration? And typically we don't concern ourselves with where if both atoms are getting the same thing. So if I'm adding a halogen, both atoms are going to get a halogen. Or if I'm making a cyclopropane ring, both atoms are involved in that ring. Or an epoxide, both atoms make the epoxide. Or if I'm cleaving the double bond, both atoms are going to gain an oxygen from that cleavage. So I don't have to concern myself there. But for all the other cases, I need to think where things are adding. And again, we think of a Markovnikov versus an anti-Markovnikov addition. And the last thing to consider to master all these reactions is how. How do these things add? Do they add to the same side, opposite sides, or is there no preference for how those atoms add?